This video goes over continuity. So in order to understand continuity, we need to understand limits because that's part of the definition. So just a couple warm-up problems. If we're looking at problem one, what we'll probably want to do in order to factor the numerator is use long division or synthetic division. So I'm going to use synthetic division. 1 times 1 is 1, 2 plus 1 is 3, 3 times 1 is 3, 4 plus 3 is 7, 1 times 7 is 7. So I end up with a remainder 0. So the limit as x approaches 1 of, I factored the numerator into x minus 1 times x squared plus 3x plus 7. So now I can cancel those off. And the reason that I had to do this in the first place was this ends up being an indeterminate form if I plug in 1. So that's an issue. So I have to see if I can cancel some stuff off. So the limit as x approaches 1 of x squared plus 3x plus 7 is equal to 11, because now I can directly substitute 1 in. Problem 2, in order to do this one, we're going to have to take the limit and realize that I also have an indeterminate form. And so the algebra way that I can deal with this is multiply by the conjugate of the thing with the square root. So then what I end up with is the numerator. The numerator ends up being x plus 4. The middle terms end up being plus and minus root x plus 4, so those end up canceling out. And then negative 1 times 1 ends up being minus 1. And then the denominator, I don't really have to do a whole lot to, because what's going to end up happening is this numerator, x plus 4 minus 1, I can simplify to x plus 3. Now I can cancel these off. I end up with the limit as x approaches negative 3 of 1 over root x plus 4 plus 1. Now I can directly substitute negative 3 in. I get 1 over root 1 plus 1, which is 1/2. So 11 and 1/2 were the answers to those two questions. Now really quickly, if I think about this one, I have this piecewise function, 3x plus 7 if f is, or if x is greater than negative 6. And if x is less than or equal to negative 6, I have 1/3 x minus 9. So to the left, that would represent this one. I have something that looks kind of like this. And to the right, I have 7, and then a slope of 3. And I'm not doing a great job of graphing it. But basically what we're trying to get at with this problem, and it's not really that complicated, like the limit as x approaches negative 6 from the left, I just plug in negative 6 here. I get negative 2 minus 9, which is negative 11. From the right, I look at this one. Negative 6 times 3 is negative 18, plus 7 is negative 11. We've learned in the past that if the limit from the left is equal to the limit from the right, that's equal to the limit in total at that value. So the limit as x approaches negative 6 is negative 11. Now, why is that important? Because the function value, at least in terms of what we're trying to learn today, the function value, f of negative 6, is also equal to negative 11, because this is a less than or equal to thing. So therefore, the limit from the left, limit as x approaches negative 6 from the left of this function, is equal to the limit as x approaches negative 6 from the right of this function, which is also equal to the value of the function at negative 6. All of these things are equal to negative 11. Since all of these things are equal, we can draw this graph without picking up our pencil. So if I trace this, as I got near negative 6, I could draw everything without picking up my pencil. So from the left, from the right, and the actual value all meet at the same spot. If that's the case, I would say that the function is continuous at x equals -6. And so that's what it means for a function to be continuous at a value a. So in that last problem, a was -6. What we were thinking about was the function continuous at -6. This function is actually continuous everywhere. Like if I did that for any value, if I did it at x equals 0, notice that from the left, from the right, and the actual value, all of them would be equal to 7, right? So f of 0 equals 7, limit from the left and limit from the right are all 7, right? So because that's true, I can say that it's continuous at 0. This function would be continuous anywhere. But the main problem that we had was at -6, because that's where we had some sort of possible debate, because we had some sort of issue at -6. So that's kind of why we were investigating it there. So a function is continuous at a value if the domain is defined there. So therefore, f of a equals some number. Then we also have the limit from the right and the limit from the left are equal to that same number. So in shorthand, this is what we would say a function is continuous at x equals a if the limit as x approaches a from the right of the function is equal to the limit as x approaches a from the left of the function, which equals the value of the function. And this basically means that you can draw f in the vicinity of x equals a without picking up your pencil. So once again, I can draw this around x equals a without picking up your pencil because the function value is equal to the limit from the left and the limit from the right. So what are some examples of things that are not continuous? Some non-examples. So things are not continuous if you have a removable discontinuity, because you would have to pick up your pencil where the hole was. And that could show up either there's no function value there or the function value could be misplaced or relocated somewhere else. So you have a hole, you have a jump, or something that looks like this. You have a gap in the function. So there is some sort of values that are missing in the middle. Or you could have a vertical asymptote. These are all instances of functions that are not continuous. So if we take a look at this graph, as x approaches -6, the function is not defined. So therefore, we already know the function is now not continuous at -6. But let's fill out the rest of the chart. Limit from the left and the limit from the right are both 5. So the value of the function, or the value of the limit, is 5. But since it's not defined there, then it's not continuous because it doesn't all match up. At -3, the value of the function is 2. The limit from the right appears to be -4, but the limit from the left is 2. Since all of these things are not the same, the value of the limit, or since these two things are not the same, the value of the limit does not exist. And therefore, since all three of these things are not the same, I would say that this function is not continuous at x equals -3. As we approach x equals 0, the limit from the left, the limit from the right, and the actual value of the function are all 0. So therefore, it is continuous at 0. What about at 2? There is no value for the function. The limit as we approach the left is infinity. The right is -infinity. This does not exist, and this is not continuous. Well, it automatically met the first criteria of not being continuous right there. At 5, it appears that the limit from the left, limit from the right, and the actual value of the function all appear to be intersecting at somewhere around 4.5 or something like that, right? So We don't know exactly what it is, but I'll just make the assumption that it's 4.5. So all of these things are the same, and the answer would be yes. At x equals 6, we have a major issue. So at x equals 6, the function value is 1. The limit as x approaches 6 from the right of the function is -1, and the limit as x approaches 6 from the left of the function is equal to 5. Since all three of these things are not equal, that would be a no. Then we also have 8 that we have to deal with. At 8, we have a hole, it appears, and it's just like this thing at 6 or -6. So -1 is the limit, but the function does not exist, and therefore it is not continuous. Okay, we have a couple more things. If we think about this graph, at -8, the value of the function is 4, but from the right and the left, the limit is -5, so it's not continuous. At -6, limit from the left, right, and the actual value of the function are all -7. Since all three of these things are the same, the answer is yes. As we approach 0, I'm sorry, -4 is next. The limit from the left is -5. The value of the function is -5, but from the right, we're approaching -2, so that's a no. Then when I look at x equals 0, the value of the function is 0, limit from the left is 0, but the limit from the right goes off to infinity, so this is not continuous. And so now that we've done some graphical stuff, now we're going to do some analytic or algebraic manipulation of limits and continuity. So we're going to take a look at problem 1. In order to determine whether this function is continuous at x equals 3, I need to look at f of 3, which we know is 1. Then I'm going to take a look at the limit as x approaches 3 from the right. So that's going to be this one here. So if I take a look at the limit as x approaches 3 from the right of f of x, that's the limit as x approaches 3 from the right of this component of the function. And that can be done with direct substitution. So I have 9 over 3 minus 1, which is 9/2. So this is clearly not continuous at x equals 3, because notice that the value of the limit as we approach 3 from the right is not equal to the value of the function at 3. But I'm also going to check this one, and I think this problem should be x squared minus 9. So the limit as x approaches 3 from the left, and actually I know it's supposed to be that. You're not allowed to change the problem whenever you want. I just know what we were meaning. So we have x cubed minus 27 over x squared minus 9. And that one is 3 from the left, because notice that x is less than 3 over here. So now I'm going to factor this. So the limit as x approaches 3 from the left of x minus 3 times x squared plus 3x plus 9. And that's the difference of cubes. You learned that in Algebra 2. X minus 3, x plus 3 is the factoring of the denominator. So then I can cancel those out, and then I can do a direct substitution. So I can now plug 3 in, and I get 27 over 6, which is 9/2. So notice that the limit of this exists. So the limit as x approaches 3 of f of x does exist. It's 9/2, because both of these are equal to 9/2. But since they are not equal to the value of the function, at that point, it's not continuous at x equals 3. Okay, so this problem has two different things going on. F of 0 is undefined, because if I substitute in 0, I get 0 over 0. So this is an indeterminate case, so indeterminate form, I'm sorry. So the limit as x approaches 0 of this function. Now, do I really need to calculate this if I'm doing continuity? No, because I already know that this is not continuous at x equals 0 because the function has to be defined at 0. But I'm going to do it anyway just to get a little practice in. So the limit as x approaches 0, if I factor this, it's x times x minus 6 over x times x plus 6. So then I can cancel the x's and I get x minus 6 over x plus 6. And then I can now do a direct substitution. Negative 6 over 6 is negative 1. So notice that this function at 0 approaches negative 1, but it has no value of the function. Now notice I didn't have to do from the right and from the left like I did in problem 1, and that's because this function approaches the same thing from the left and the right. It approaches this function. It's only defined in one way, whereas this function is defined in multiple ways in a piecewise function. So I don't have to really separate it into from the right and from the left because it's the same thing from both sides. So now let's deal with 1. F of 1, I can just plug in 1 and I get negative 5/7. And also the limit as x approaches 1 of this function. Once again, there's no problem. It's not an indeterminate form. I can literally just plug in 1 and I get negative 5/7. So the function is continuous at x equals 1, and it's not continuous at 0. Problem 3, f of 5 is equal to 18. And then the limit as x approaches 5 of f of x. Well, now I have to take a look at this 2x plus 8. That I can use direct substitution. I also get 18. So since f of 5 is equal to the limit as x approaches 5 of f of x, this function is continuous at x equals 5. Problem 4, it's a piecewise function. So the first thing I notice is that f of 0 is equal to 2. I'm determining this at 0. Now the limit as x approaches 0 from the right, so x approaches 0 from the right, that's going to be this one over here. So that's the limit of the function would be 2e to the x. This is also a direct substitution situation. So 2e to the 0. Remember, anything to the 0 power is 1, basically, so 2 times 1 is 2. Both of these are 2, so I can continue and see what happens as the limit as x approaches 0 from the left. So I'm going to factor out the x squared in the top. And then I can cancel these x squareds. And now I have a direct substitution situation. So the limit as x approaches 0 from the left of x plus 2, I can just plug in 0, and that's 2. So the limit from the left, limit from the right, and the value of the function are all the same. They all equal 2. Therefore, it is continuous at x equals 0. Finally, I'm going to look at problem 5. F of 0 is 1. Then I want to do the limit as x approaches 0. I only have to do it once because it's approaching the same thing from both sides. So I'm going to factor out an x, then cancel the x's, and then do a direct substitution. I get 3 over negative 3, which is negative 1. Notice that 1 and negative 1 are not the same, so this is not continuous at x equals 0.